It is important for us to precisely describe each collection operation. But while we can easily describe operations for collections of a specific size, it is difficult to generalize the descriptions to collections of all sizes. To illustrate this, let's try to describe the prepend operation. Here are some examples. After 5 is prepended to list 34, the new list is 534. After 7 is prepended to list 1113, the new list is 71113. Notice how similar they are. Perhaps we can construct a single property that describes the prepend operation for all possible lists. We can start by using variables in place of values. The property is now, after X is prepended to list AB, the new list is XAB. This property describes what happens when we prepend any element X to a list with any two elements A and B. Using this property, we can verify claims such as, after 65 is prepended to list 6157, the new list is 656157. And after 17 is prepended to list 1923, the new list is 171923. How about when the initial list length is 3? For example, after 2 is prepended to list 345, the new list is 2345. We cannot apply our property to verify this claim, because the property only applies for lists with two elements. To prove the claim above, we need a new property. After X is prepended to list ABC, the new list is XABC. This looks similar, but the initial list length is now 3. How about when the initial list size is, say, 10? For example, after 0 is prepended to list 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, the new list is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We need a new property with initial list length of 10 as follows. After X is prepended to list A, B, C, D, E, F, G, H, I, J, the new list is X, A, B, C, D, E, F, G, H, I, J. It appears that we need to create properties for every possible list length. But this is impossible, since lists can be arbitrarily long. Is there a way to construct a finite number of properties, ideally 1, that covers all list sizes? How about this one? To prepend X to a list L, put X in the front and L after that. This describes an algorithm, or a recipe to prepend an element, but it doesn't specify the result of the prepend operation. Let's highlight the issue by plugging in some numbers. For example, to prepend 3 to a list 4, 6, put 3 in the front and 4, 6 after that. This sounds fine, but this claim does not tell us what the new list looks like. Here's another attempt. After X is prepended to list L, the new list is X, elements of L. This time, the issue is more subtle. What exactly is elements of L? We want L without the brackets, but a list without brackets is no longer a list. But elements is also not a single value. Let's again plug in some numbers. After 3 is prepended to list 4, 6, the new list is 3, elements of 4, 6. This claim does not quite contain the result of the prepend operation, so we are left to guess. Is it the list 3, 4, 6? Or is it the list 3 and a child list 4, 6? Or is it something else? We made a few attempts to write a general property for prepending an element and failed. Is there another way? Let's see if we can construct a prepend property with logic walk stacks. As before, let's begin with a two-element collection. For example, After 5 is pushed to stack 3, 4, the new stack is 5, 3, 4. We replaced prepended with pushed, since prepending to a list is equivalent to pushing to a stack. Here is the property for any stack of length 2. After A is pushed to stack BC, the new stack is ABC. Next, let's try a 3-element collection. For example, after 7 is pushed to stack 8, 9, 10, the new stack is 7, 8, 9, 10. Do we still need one property per stack length, or can we create one property that covers all stack sizes? Please take a moment and see if you can come up with a single property. Here's a hint. Try combining the 2-element property and the 3-element property. The logic walk stack prepend property is, after X is pushed to stack Y, the new stack is XY. Let's try to prove some claims with this property. Here's an example with 2 elements. After 7 is pushed to stack 11, 13, the new stack is 7, 11, 13. In the example above, X is 7 and Y is 11, 13. It fits perfectly. Here's another one. After 36 is pushed to stack 7, 11, 13, the new stack is 36, 7, 11, 13. In this example, X is 36 and Y is 7, 11, 13. Here's a very long one. After 0 is pushed to stack 1, 2, 3, 4, 5, 6, 7, 8, 9, the new stack is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. In this example, X is 0, and Y is the stack 1, 2, 3, 4, 5, 6, 7, 8, 9. Finally, here's an empty stack. After 7 is pushed to stack empty, the new stack is 7. In the example above, X is 7 and Y is the empty stack. As we can see, the property even works with an empty stack. It appears that we successfully created a prepend property that applies to stacks of all sizes. The property is quite simple and elegant. And this is no accident. We designed logic walk stacks specifically to describe collection operations. We intentionally defined the stack as a 2-element list, since it is easy to construct properties with fixed length lists. Interestingly, this trick works even though the second element is another list. As we just saw, we cannot be as precise with lists as we can be with logic walk stacks. Therefore, we will only use logic walk stacks to describe collection operations. Next, let's try to describe other operations such as removing and finding elements.